I remind you that we are recording this seminar as usual. So today we have two speakers remote. It's my pleasure to introduce you the first one, Joris Witstok. So he's currently a Dawn fellow at the Cosmic Dawn Center affiliated with the Niels Bohr Institute at the University of Copenhagen in Denmark. He obtained his PhD at the Cavendish Lab in the University of Cambridge in UK, supervised by Renske Smith and Roberto Maiolino. And before that, he completed the undergraduate studies at the Leiden University in the Netherlands, where he's originally from. And today he's going to talk us about witnessing the onset of the reionisation, the Lyman-α emission, in distant galaxies. So, Joris, the floor is yours. And I'll give you 5 minutes warning.
Yeah, okay, well, thank you so much for the introduction, and thank you for having me today. I'm sorry I can't be there in person, but I'm very excited to show you some of the latest results we got mainly as part of the JADES collaboration that I'll be talking about today. So yeah, my name is Joris Witstok. Currently a fellow at the Dawn Institute, and let me first also thank all the people without whom all this work wouldn't be possible. So in this case, that's the JADES collaboration, and I just want to highlight a few people here in this was a pretty grey day in Oxford, but two of the junior postdocs, so Gareth Jones and Ayush Saxena, who we've been doing this work on Lyman-α emitters within the JADE survey and so just to give you a bit of context, so what I think is really fascinating, the things we can now start to study with JWST are, of course, the very early stages of galaxy evolution and reionisation that was coupled to it. So when we kind of zoom into this timeline, as you probably know, the lambda CDM cosmology tells us that the first dark matter halos start to collapse during the dark ages, and that leads to the formation of these first stars in the universe, the first astronomical objects. And there's two things that very quickly happen because of that. So first of all, these stars start to emit a large amount of ionizing photons. But secondly, they also start to pollute their surroundings with heavy elements. So carbon and oxygen are all being produced in these stars and being spread in supernova explosions. And that also marks the transition of this pristine first generation of stars, the population 3 stars, to the subsequent generations. And if we look a little bit further than that, so we think that the first objects formed maybe at a redshift of about 20 or 30, so that's a few 100 million years after the Big Bang. And a few 100 million years after that, we know that the universe had been completely reionized in terms of the neutral hydrogen that had all been largely, to a very high degree, been turned into ions. And that's a process that we can track using the Lyman-α transition. So it's been very well known that this is a very, very bright emission line usually for galaxies. But the one thing is that it's very, very sensitive to being scattered in neutral gas. And so that's kind of depicted in this cartoon here. So as a reionization front passes through the universe, we can see, for example, going from the orange galaxy on the left, which is where the ionization front has already passed. The Lyman-α emission, as shown in the spectrum, will be observed by us, but for galaxies that are still surrounded by some neutral gas in the intergalactic medium. This means the Lyman-α emission gets completely absorbed. And so we see this observationally. This has been known. If we look at the fraction of galaxies that are seen as Lyman-α emitters, or LAEs, that fraction very rapidly drops if you go beyond a redshift of about 6. And so that's seen as a sign that the universe wasn't completely reionized before then. So there was still some residual neutral gas in the IGM. At the same time, now with JWST, we're able to go even beyond that. And what's been very interesting is we see some of the most distant galaxies, particularly above a redshift of about 10, which show this very, very strong damped absorption signature, seemingly. So here the light blue lines show you what you would expect just from a mean IGM absorption, whereas the red line is a fit showing what you would expect if you get something, some very, very dense neutral gas surrounding this galaxy. One other possibility, though, and I'll talk a little bit more about this later on, is nebular-dominated spectra. So if your nebular emission is completely outshining the rest of the galaxy, the two-photon continuum can also produce a shape like this, or very similar to a DLA kind of absorption. And so this is, I think, yeah, something we can start to look into more and more with the JWST data. So as mentioned today, I'll be presenting some of the data specifically from the JADE survey. So this is the JWST Advanced Deep Extragalactic Survey, a joint program from the NIRCam and NIRSpec GTO teams. On the right, you can see a nice image over the iconic Hubble Deep Field, but as seen now by the very deep NIRCam imaging. And so what the goal really of the survey is to take this very deep imaging and then select high redshift galaxies from this and put slits over them to observe them with the NIRSpec multi-object spectrograph. And we do this over the two goods fields. And what this has produced is spectra like these. So this is a redshift 9.4 galaxy observed across different spectral resolution modes for nearly 100 hours. And so you get these beautiful, very, very high signal to noise data, and all of these, the wiggles you see are now really, emission lines and signatures that we can start to do physics with. So this is really, really incredible. And what we could already do quite early on is look at some of the Lyman-α emitters in the JWST data. And this is shown here. So the squares are all the Lyman-α emitters that we see right about a redshift of 5.9 in the good south field. And it turns out all these Lyman-α emitters coincide quite well with overdensities that we can identify using the slitless spectroscopy from the NIRCam instrument. And I think, yeah, this is probably not a coincidence, because we are seeing this all over the place, and is really telling us that these regions that are sufficiently reionized for us to be able to see Lyman-α are probably always overdense, just because there's more galaxies there and they've been able to reionize their surroundings more quickly. So one of the surprises in the JADES survey early on was this galaxy you might have heard of called GNZ11. So it's shown in the highlight image on the top. And what was the surprise is that when we took a spectrum of this galaxy, we were able to see Lyman-α at a redshift of 10.6. And this was really quite unexpected. And after that, there's been, of course, many more galaxies we're able to observe. And so this is just a small compilation of their UV magnitude versus the redshift. So the brighter objects are at the bottom, and the fainter ones at the top. And the Lyman-α emitters include these three beyond a redshift of 8, and that was again quite surprising. So you see GNZ11 all the way at the bottom right, and then previous mostly ground-based efforts were able to see some Lyman-α emitters between a redshift of 7 and 8, so those are in the bottom left. But then as we looked at some of these fainter sources, it turned out actually some of them also had Lyman-α emission, and some quite strong Lyman-α emission even. And so this is, accounts to 3 new Lyman-α emitters on top of only 2 that were found before. So it's probably a signature of these early ionized bubbles. And with NIRSpec, we get this full view of the whole spectral range, so from the UV to the rest optical. And just to point out a few things, I won't go through all the details, but we see that indeed the nebular emission in these objects is quite strong, which we see from the Balmer jumps in their spectra. And we also see very high ionization lines, so carbon-4, requiring more than 54 electron volts, showing these objects have quite hard radiation fields. So what is this really telling us? Well, before getting into that, I just want to quickly talk about AGN activity. So again, going back to this GNZ11 object, there's actually some evidence that this is also hosting an AGN. And what it's telling us that is there's several very high ionization lines, as well as a C2 line typical of AGN activity. When we look at some of the ratios of these lines, they're also pointing towards very, very high density, so above 10 to the 9, which is, normally only seen for AGN. And also this very deep blue shifted carbon-4 absorption. But that is in GNZ11, which is one of the brightest galaxies. So I think one challenge in these high redshift studies has been, how can we select AGN in typical galaxies, which of course traditionally used to be done with, the BPT-like diagnostics like these. But it turns out if you do that at a high redshift, and I'm sorry for all the points on this, but the point is basically all the points line up on top of each other, and whether it's an AGN or a star former, they kind of land in the same region of the BPT diagram. So this becomes very, very tricky. The other kind of puzzling thing, which might be connected, is this lack of X-rays that, we can't explain very well. I don't think I have the time to go into the details here, but essentially there's two, there's probably different scenarios we could imagine to explain this weakness, but I think one interesting connection is that if, for example, the BLR shows very, very dense gas column densities, that is actually also something you would expect from the self-absorption we see in some of the Balmer lines in these broad line selected objects. So again, happy to chat more about this later. But for now, back to the Lyman-α emitter. So how can we tell if there's AGN activity in those? Well, in this case, we looked at some of the new UV line diagnostics. So again, I don't have time to go into all the details here, but essentially we see that the very strongest Lyman-α emitter at very high redshift is still clearly consistent with what we expect from star formation. But there's also some indication for another Lyman-α emitter that it could be hosting an AGN. So it's kind of a mixed bag between these Lyman-α emitters. If we then go on to their stellar properties, which of course has the caveat that we're then interpreting their light as being stellar, we see that all of them are very compact, highly star-forming galaxies. So they all show in their star formation histories this characteristic, very strong upturn in very recent, so very young stellar ages. What's also striking is that all three of these are showing some indication of very close by neighbors, and so that might point towards a sort of merger-induced star formation burst. And then,
Joris, so this your 5 minutes warning.
Yeah, okay, thanks. If we then start to look at how these relate to their Lyman-α properties, one quite interesting trend is the one where we compare the Lyman-α strength, so the equivalent width on the y-axis, to the star formation surface density. And so in the background, so the green small circles are all local analogs, so local sort of metal poor dwarfs that we think might be somewhat like the very high redshift galaxy population. And indeed, two of our points, so the orange and green hexagons, do align with that, with those populations. But you can see this blue point, the highest, the strongest Lyman-α emitter, clearly occupies just a completely different regime of star formation. And the same is true for GNZ11, although its Lyman-α strength is slightly lower than this one. But this general trend between the strength of Lyman-α and this star formation intensity in some way is probably telling us that this compactness of these objects, which implies such a high intensity, is probably key to helping escape the ionizing photons and Lyman-α through channels, for example, created by feedback processes. And so in the last few minutes, I just want to spend on this very puzzling object, which is something we found, we put out a few months ago. So it's, again, a very, very compact galaxy. One of the best very high redshift candidates we had. And when we took a spectrum of it, it indeed was confirmed to be at redshift 13 based on the Lyman-α break. But very surprisingly, it showed this very bright Lyman-α emission line at the same time as showing this sort of smooth turnover in the continuum, which again has been seen in other galaxies, although they didn't show Lyman-α emission, but this kind of DLA, so damp Lyman-α absorption like signature. So what can we tell from just this one line? Well, it turns out it gives us pretty interesting constraints, because being at redshift 13, that means the Lyman-α has to survive through so much of the neutral IgM that unavoidably some of it will be absorbed. And so that means the fact we're seeing such a bright emission line still must mean the object is a very, very efficient, has a very efficient production of ionizing photons. And this is really kind of starting to push the boundaries of what we think, stellar populations are able to produce. And at the same time, what it's also showing, if this Lyman-α is able to get out and be observable, it probably means this galaxy is located within some early ionized region or early ionized bubble that's accommodating the escape of Lyman-α photons. So putting this all together, this is quite challenging to explain, and I'll try to illustrate kind of why, we have a lot of question marks around this object. So just in the rectangles, they're shown, two possible scenarios that could explain all the observables. So the observables being the bright Lyman-α emission, the strong turnover in the UV, and finally also this object having a very, very blue UV slope, while we don't detect any helium-2 emission. So first of all, this bright Lyman-α emission means there's a lot of ionizing photons, and probably the line needs to be offset from the systemic and potentially being helped by this ionized bubble. So the ionizing photons can both, the production rate could be explained by something like very massive stars and also an AGN. The AGN might also help explain the large velocity offset, if that is there. Then going to the UV turnover, this, as I mentioned, has been explained as a DLA signature, or it could be this two-photon continuum. So if we look at the DLAs, well, that potentially, seems seems at odds with this very strong Lyman-α emission. How can you have this very strong absorption of the continuum even if the line emission is coming out? But then again, maybe some disk-like morphology, geometry could explain having both the DLA and potentially a more extended region that's emitting in Lyman-α. But if we look at the two-photon continuum, that's consistent with the high ionizing photon production rate, but then that's seems inconsistent with the very blue slope, because if the nebular continuum is very dominant, that actually reddens your slope, so making it inconsistent with what we measure. So the slope we measure could be explained by an AGN that's being a disk that's been truncated, which has been observed in some cases. At least our models of POP3 stars don't allow slopes this blue, so that's really kind of a puzzle. What could be happening, though, is a very high escape fraction of ionizing photons, which, again, helps in the scenario of creating this ionized bubble. But so just to illustrate that, there's a lot of question marks here about what is possible at the same time as something else. So I think, this object has really kind of introduced a new, very interesting debate on what we're observing. And with that, I'll just conclude to say that Lyman-α, all the way very deep into the epoch of Reionisation, is providing us with new insights about the nature of these early galaxies. I've shown you some results of 4 different Lyman-α emitters, which are all very compact, probably very highly star-forming, low-mass galaxies. And this new population of Lyman-α emitters, which are at the same time showing this strong turnover in the UV, is really a puzzle to explain. And so, with that, thank you very much, and happy to hear your thoughts and questions on this.
Thank you. Do you have any questions for? Sure.
Do you have an idea of how typical these objects are of all of the objects, this redshift, or do you not yet have any idea of that?
Yeah, well, that's a very good question. So there's of course, not been that many galaxies confirmed above redshift 10, 11 at all. So there's, I think at the latest count, something like 10, 15 that have been confirmed. So in that sense, very small number statistics, it could be as high as, say, 10% at that regime, or, we've just been very, very lucky, but that seems maybe less likely. At the lower redshifts, though, there have been more systematic searches, and yeah, there's been some papers on trying to quantify or find more of these objects, and there's definitely a population of them. I can't quote a specific fraction at the moment. They still, they're definitely not a dominant population, but yeah, we are definitely finding more and more of them. I hope that answers the question.
Thanks. More questions?
Hey, Joris, it's Jake Bennett here.
Hey.
My question is about kind of the compact objects that you're finding, because do we see such compact things at low redshift? And I'm kind of wondering, like, if not, where do they go? And what happens to them?
Yeah, that's a good question. So I guess there's two things. So there's the objects being very compact, but also being bright enough for us to detect them. So yeah, for example, here you can see in terms of the star formation rate surface density, some of the high redshift objects are definitely above what are, these local analogs, which are already very extreme and rare objects in the local universe. So I would say in that aspect, well, they only seem to be around in the high redshift universe. This redshift 13 object, for example, has a size of about 60 parsec. And yet it's forming stars at something like a solar mass per year. So this is, just, which is, comparable to the Milky Way. So it's a very different regime. I wouldn't know where they go towards later times. That's a good question.
Thank you. In the interest of time, let's thank Joris again.
Thank you.
And let's move to the second speaker. If you can share the screen, you want me to.
It's okay. Can you see and hear my?
Yes.
Can you see my screen and hear me? Great.
Okay, so our next speaker is Freek Roelofs. He obtained his PhD from Radboud University in the Netherlands in 2020. He was a Black Hole Initiative Fellow and a postdoctoral researcher at the CfA until this past August, and has recently moved back to the Radboud University as a postdoc. Freek is an expert on VLBI data analysis and has worked on synthetic data generation, polarization and dynamic analysis techniques, and space mission development in the context of black hole imaging. He is an active member and a project coordinator within the Event Horizon Telescope collaboration. Today, he will talk about studying material fields, dynamics, and fundamental physics near a black hole with the current and future VLBI instruments. So, Freek, you can go ahead.
Okay, thank you very much, and thank you for the invitation to speak here, and very nice to be back at the CfA, even if it's virtually. So black hole imaging is what we do with the Event Horizon Telescope, and we have imaged these two black holes in total intensity and polarization. On the left, we have M87, 6.5 billion solar mass black hole in a giant elliptical galaxy, which is also emitting a large-scale jet. And on the right, we have Sagittarius A star, much smaller black hole, 4 million solar masses in the center of our own galaxy. And despite the difference in mass and environment, we see that the black hole images look quite similar. We have this ring of light, and on top of that, this a twisty pattern in polarization. And I want to talk a bit more about how we got these results, especially the polarization results for these black holes. So the EHT is a VLBI array. It consists of sub-millimeter telescopes across the world, and we measure visibilities, which are Fourier components of the image on the sky, on each of these baselines between two telescopes. And the more of these baselines we have, you can see them plotted here in this UV plane, the higher fidelity image we can reconstruct. And the resolution of this image is set by the longest baselines and the observing frequency. So in our case, this is really limited by the size of the Earth. So I want to talk mainly about polarization. And if you want to understand what is happening near a black hole, measuring polarization and imaging it is very important. It traces magnetic fields, but in addition to that, it's also affected by GR effects, so light bending around the black hole, and plasma properties, for example, through this process of Faraday rotation, where the EVPA, the polarization angle, changes as the photons propagate through a magnetized medium. And here in these simulations, you can see that the polarization pattern on the ring of light can probe the black hole spin. So you're going from an azimuthal EVPA pattern for a zero spin black hole to a more radial pattern to a high spin black hole as the magnetic fields are wound up around the black hole by the rotating spacetime. And it's also a probe of the accretion state. So with the EHT polarization data, we were able to rule out many of these sane models from our model library, which have weak magnetic flux and a turbulent polarization or magnetic field structure. And we are favoring now these MAD models with strong magnetic flux and ordered polarization structure, as you could also see in the M87 image. We also look at circular polarization. Circular polarization is also an indication of the magnetic field strength, and it's a sign left or right. Circular polarized indicates the magnetic field orientation. You can see that in these simulations here, where you're looking at the black hole and jet from opposite viewing angles, and you see an overall sign flip in the circular polarization. And on the bottom, you can see here in this simulation that you can see these different regions of circular polarization emission tracing this magnetic field configuration of a helical. There's a helical magnetic field structure here, and it's going in and out of the page in these different regions, and the circular polarization emission actually traces those regions. But circular polarization also depends on a lot of complicated plasma effects, and in particular, circular polarization can be generated through Faraday conversion, where the linear polarization is converted into circular polarization depending on the plasma properties. So there's a lot of plasma physics in the circular polarization structure as well. So in this project, I've been trying to approximate the image structure in both total intensity and polarization using a technique called geometric modeling. And in this technique, we, instead of doing a full VLBI imaging approach, we fit a simple geometric model that depends on only a few parameters to our visibility data. And this gives you measurements with error bars of parameters that we're typically interested in, for example, the ring diameter or the ring thickness. And it can also help to provide constraints where a full imaging approach is not really viable. We've been fitting this M-ring model to the data, and this M-ring model is just a geometric ring model. And then along the ring, we add these Fourier modes parameterized by these complex betas. And by adding more and more of these Fourier modes, you can make a more and more complex azimuthal structure along the ring. You can extend this to polarization as well. And then what's especially interesting is this beta 2 mode, which is probing this twistiness of the polarization pattern. And as I showed a few slides back, this twistiness can be a probe for black hole spin. So I've applied this M-ring modeling in linear polarization to the M87 data from the EHD from 2017. Here you can see on the 4 days that we observed M87, the average images from different image reconstruction methods. And now in this row, you can see the M-ring model fits to the same data. And then you see when we blur them to the same resolution as these images, you can see that the polarization pattern in these simple model fits is really quite similar to what we see in the EHD images. So we can really reproduce all the information.
Similar to Eastleigh. Check it out.
Sorry for them.
Okay. So we can really represent this polarized emission with a low-dimensional M-ring model. We also looked at circular polarization, and circular polarization signal is really very weak. It's about a % level signal, and that means that we really need to rely on robust data products that are not sensitive to calibration errors, which could introduce spurious circular polarization signals in our data. And one of the data products that we look at is the closure phase, which is the sum of visibility phases on a triangle of baselines where station-based errors like those introduced by the atmosphere, which is bothering us a lot, just cancel out. And what's interesting is that if we look at 2 different correlation products, so our antennas at the different sites measure the right and the left circular polarization. And if you correlate right and right of 2 antennas and left with left, you look then at the closure phases and you see a difference between those 2. That is an unambiguous signal that there is some interesting circular polarization structure on the scales that you're probing with these baselines. So in the EHD data for the M87, we did indeed see a significantly non-zero offset between these right and left closure phases, which means that we have detected circular polarization structure in M87 on scales of the event horizon. So now that we know that we have detected the circular polarization structure, the next question becomes, of course, can we image it and say something about the structure? And as you can see from these results here, the answer is unfortunately not really. We see here for different days, a different EHD observing band, different imaging methods from left to right, and on the far right is our M-ring geometric modeling. We see that the image structure really depends on the imaging methods, the band, and the days. You can see it also here for April 10 and 11. So we had to conclude that we cannot really get a circular polarization image of M87 yet, but this analysis did allow us to establish an upper limit for the resolved circular polarization fraction in the image of 3.7%. And this already can tell us a lot. We see that this is consistent with simulations in our GRMSD library, and that again, independently of the linear polarization, is strongly favoring these math models with high magnetic flux. And we see that the dominant circular polarization production mechanism in these models is Faraday conversion. So we're really looking at circular polarization here that is originating from these plasma effects. Looking again at these different images, we do see that where all the imaging methods are showing quite varying structure. The geometric modeling results on the far left column are showing this same structure independent of the day and the band with negative Stokes V here in on the south side and a bit to the west of the image. Here this was an m=1 fit, which means that we only allow a structure that is as complex as a dipole, but we can challenge this model a bit more. And here we go in the different rows from m=1 on the different days to m=2 and m=3. So here, for example, for m=2, we allow a quadrupole structure in our model, but still the data favors this dipolar structure in the circular polarization. And even if we go to m=3, especially for April 11, we still see that this dipole structure is favored. So we cannot confirm this yet with the full imaging methods, but there does seem to be a preference in the data for this kind of dipole structure in the circular polarization. So this will be very interesting to look at with an enhanced and extended EHT, where we can hopefully make full circular polarization images of M87. Moving on to the other black hole, Sagittarius A star. For Sagittarius A star, we have the issue that we are dealing with rapid variability. So the source is changing a lot as we observe it. And for that, we use different techniques. These imaging methods are adding a variability noise budget to the data before imaging. With the geometric modeling, we take a slightly different approach in that we use snapshot modeling. So we're fitting our model to 2-minute snapshots of data separately, and then combine the posteriors to obtain an average structure here. And you can see here these different approaches all agree on the polarization structure of Sagittarius A star with this twisty polarization pattern again, but going into the other direction actually than M87. And we see that the polarization fraction here is quite large. It can reach up to more than 30% or so. And this again favors these MAD models with high magnetic flux and ordered polarization structure. We also looked at circular polarization in Sagittarius A star, where we again measured in the closure phases an offset between these right-right and left-left closure phases, which means that also for Sagittarius A star, we have detected horizon scale circular polarization. We try to image this with the different methods. There is again a lot of uncertainty in the image, although all the methods do reconstruct this negative Stokes V here on the right, and two of the methods, the M-ring modeling and TEMIS imaging, also are reconstructing a positive Stokes V component and a sort of dipole structure. But overall, there's still quite some uncertainty in the image here. So now that we have imaged these two black holes in polarization, the question is, what's next? There's a lot that we can still do in enhancing and improving and extending the EHT, and this is planned in the next generation EHT project, which aims to build many more sites and observing at 3 frequencies simultaneously, so 86, 230, and 345 gigahertz. And then you get these very nicely filled UV planes, and with that you can really move from black hole imaging to black hole movie making. And these are some results from the NGEHT analysis challenges that I ran, where we generated synthetic data from different models for M87 and Sagittarius A star, and then released those data sets and then asked different imaging teams to reconstruct movies out of these. And here you can see some of the results. Here you can see the M87 jet being launched. We see the GRMSD model on the left and the reconstruction on the right. So you can really trace these jet wisps propagating out. And on the right, you see for Sagittarius A star, where the variability timescale is almost shorter. within an hour or so, we see this hotspot appear and shear out. And with NGHD coverage, we could also trace that. So still a lot of exciting things to be done from the ground, but I also want to talk a bit more about going into space.
You have 5 minutes left.
Okay. So beyond the NGHD, we are really limited by the Earth's size and the atmosphere, which makes going to much higher resolutions than 50 microarcsecond very difficult. So in space, we can extend these baseline lengths beyond an Earth diameter and also access higher frequencies because there is no atmosphere in space. And there is really a lot of unique and exciting science to be done from space, especially in fundamental physics and measuring what we call the n=1 black hole photon ring. And I'll show in this animation what we mean by that. So the current EHT image is really dominated by what we call n=0 emission, which is light that has been deflected by the black hole, but it's not fully orbiting around it. So the image that you see has a lot of effect from just the plasma, the astrophysics around the black hole. But part of our image also consists of light that has orbited the black hole one or multiple times. And all this emission is lensed into this thin photon ring. And by measuring the size and shape of this photon ring, you can directly measure the black hole spin and put constraints on theory of gravity. And to measure this thin photon ring, you really need to go to space. So then you can start thinking about how are we going to do this. You can do either a space-to-space array, where you launch 2 or more dishes, or space-to-ground, where you launch 1 dish and observe together with ground. Advantages to both of these. With space-to-space, you can access these higher frequencies. You're completely independent from the weather and ground side availability. But you're quite limited in sensitivity because you can typically launch only small dishes, while with space-ground, you can really leverage the high sensitivity ground-based telescopes that we have. And space-to-space is much more complicated. This has never been done before, and we need to demonstrate the technology, while space-to-ground PLBI has been done before, for example, with the Reionisation mission. Space-ground, there is a lot of activity going on right now at the CfA with the preparation for this Black Hole Explorer mission, which aims to launch a single dish going out to very long baselines that can probe and measure this thin photon ring. You should definitely ask all your CfA colleagues about this, who are really the experts. I do want to talk right now a little bit more about this space-to-space concept called the Event Horizon Imager. This is consisting of 2 or 3 satellites in medium Earth orbit with a slightly different radius. And then in the UV plane, as they orbit and drift apart, you can see you get this nice spiral shape. So you're really measuring all the Fourier components in your image up to the maximum resolution, in this case, of 3.5 microarcseconds, and compare that to the EHT resolution of about 23 microarcseconds. So here you can see some simulations of the kind of images that you can get with this. This is very much limited by sensitivity. So with a small dish, after 1 month of observing, you can start to see the photon ring here. But if you could really launch large dishes observing at these high frequencies, then you start to see this thin photon ring, which will help a lot in fundamental physics constraints. And for M87, where the timescales are much longer, you can actually play with the orbit separation so that you can fill the UV plane on a timescale that is short enough to make movies of M87. And here in these simulations, you can see if you go to large dishes, you can hardly see the difference between the model on the right and the reconstruction, the model on the left and the reconstruction on the right anymore. But this will be quite complicated, and there's a lot of technology that needs to be developed and demonstrated in space. So that is why now in a new project, we are starting to think about going towards a first space-to-space VLBI experiment. And the idea is to launch small, up to a meter or so, dishes, imaging jet at a much longer wavelength, centimeter wavelengths, where things get much easier. This is a project and some studies that we just started very recently. So this concept is still very open, and we're very much open also to new science ideas for a concept like this. Here, finally, I'll show just one first test case that I ran for observing the quasar 3C279 at 22 gigahertz. Here we can see an image that has been observed with a Reionisation, which is an existing space VLBI mission, imaging these jet spiral helical filaments. Reionisation was a 10-meter dish observing together with the full ground array up to 7.6 gigalambdas. And here in this simulation, I just took 2 small dishes in medial orbits with somewhat realistic noise temperatures. And we can see using an EHD imaging algorithm from the simulated data, we can actually see many of the same features here, which is these 2 small dishes and this much shorter baseline than what was possible with Reionisation. So this is looking quite optimistic, but there's still a lot that needs to be done in narrowing down this first demonstrator concept through discussions with ESA engineers, which are ongoing. We're going to do some more simulations with other models and explore more science cases. But all in all, I think the prospects for black hole imaging and movie making are really great. We have a lot still to do on the ground, and also for space with BEX and the EHI. There's a lot of activity moving really towards these fundamental physics measurements. And I'll leave it at that. Thank you.
So, do we have any questions? Yes.
So are you thinking of this as a possible M-class mission? Is that the scale that you would expect, or would it have to be an L-class?
For the Event Horizon Imager, hopefully that could fit in an M-class mission. That still needs to be worked out, but it looks like that might be possible. This first space-to-space VLBI demonstrator at centimeter wavelengths hopefully can be much smaller scale, because the dishes will be much smaller. We're thinking right now they might even fit on constellations of CubeSats. So that could be hopefully a much smaller scale mission with a shorter time scale, while the full Event Horizon Imager will indeed be much larger and a longer time scale project.
Any more questions? Please remember that both our speakers are available online, so there's spots in their spreadsheets if you would like to meet with them. So let's thank both our speakers again. Thank you all very much.
Thank you.